So today is also going to be about active galactic nuclei. And I was a bit worried that nobody would show up because it's AGN, but given that it's a transients focused conference, but thank you for coming.
Be warned, Barry. There's been a lot of AGN derision going on, so you know it's going to be a hard sell this morning.
Oh, okay. Well, hopefully you tell me at the end.
Yes. No, so the argument I usually like to make to people is that if you're hoping to use LSST to find any type of rare transient, you have to know what AGN are, because those are going to be your biggest contaminants in these searches. So in order to find the gold, you have to know what the other stuff around it looks like. So I'm not saying that AGN are not gold. Yes.
So I'm going to say there is plenty of gold in AGN. And hopefully I will make that case to you.
Yes.
There's lots of exciting stuff to see.
All right, so. Challenge accepted.
All right, cool.
Okay, so today we'll be hearing our first lecture by Barry McKernan. Barry got his undergrad degree at University College Dublin, then went on to do a PhD at University of Leeds, and has been at the City University of New York and the American Museum of Natural History. So Barry works on the theory of AGN, accretion, and a wide variety of things. And today we'll be telling us about what can we do with AGN variability with LSST.
All right, cool. Thank you, Kishley. So I'm going to try and keep this, like, I'll be running through too many things, obviously, right? But I'm going to try and keep it as interactive as I can. So I will ask you questions at various points and see what you think. If I can make sort of intuitive leaps. This is an outline of what I'm going to do. Hopefully we'll spend a bunch of time down here, and hopefully with this last stuff, the exciting things to search for and what can you do, you know, you'll get some ideas and thoughts, and you'll see how exciting AGN actually are. Okay, so let's start with AGN. Why do we care? So I'm just popping up some pictures of some AGN. Maybe these are contaminants for you, but this is 3C273. So this is the first sort of canonical quasar. Here are some safer nuclei. And sort of before I dive into what these things are, what's going on, I just sort of want to get a sense from everyone here. Why do we care? So what I'm going to ask you to do is talk to the person next to you and come up with some reasons why we should care about AGN. And I can wait, that's fine. So go ahead and talk.
So rude.
I know.
Oh, glare on the thing. Okay, I'll ask you.
Well,
So I'm asked to turn the lights off in front so there's less of a glare.
also, right, if you're more an AGN.
And then
planetary I think are on the easier side to understand.
Environmental study. Yeah.
Sure, yeah.
Yeah.
I don't know, they're good.
Yeah. For me, they tell me to like shoot over like a black hole in the galaxy. Because we don't know which one formed first.
Yeah.
No, we don't know what came first, the black hole or the galaxy. Yes.
Right, it's easier to measure the mass. But if you want to understand I think also,
Oh yeah. Oh, I know.
It's like,
So let's hear some thoughts. Let's hear some ideas. So why should we care about AGN? So did anyone come up with sort of anything interesting? There was a lot of talking, so there must be some ideas, right? So,
I think your reasons are better than mine.
They might be a great place for getting gravitational wave sources because you have all these things in the disk
Okay.
that might be driven to merge.
right. Okay, so potentially a source of binary black hole mergers. We'll get to that. Anything else? Yeah.
Maybe black hole demographics, maybe at high redshifts.
So if you want to understand what the universe was like, so supermassive black holes in the early universe, yeah, sure. Anything else?
Important for galaxy evolution.
Important for galaxy evolution, yeah. Like we think, if you want to know why galaxies look the way they look, these things are important, right? Anything else?
They also play a role in star formation and shutting off, or just where it happens.
Right, sort of tying into how we think galaxies look, right, in quenching star formation. Anything else?
Cool jets.
Hmm?
Cool relativistic jets.
Cool jets. Yes, there are jets. I won't spend a ton of time on jets, but yes, they have cool jets. So I'm going to say, yeah, like broadly, those are sort of some of the reasons we should care. So the very first thing, if you look at the Hubble ultra deep field, you see everything in this is galaxies, right? There are blue star forming galaxies, there are red and dead galaxies. And if you want to turn the blue star forming galaxies into the red and dead galaxies, we think that AGN play a very important role in quenching star formation, as was pointed out. And so this is our sort of theory of structure formation in the universe, so lambda CDM. So AGN seem to be really important in making galaxies or turning them into the things that we see today. If you're interested in supermassive black hole growth, AGN are incredibly important, right? You can deliver gas onto the central supermassive black hole, but also you can sort of drag two supermassive black holes together to merge and grow the black holes that way. So if you're interested in supermassive black hole growth, either in the early universe or in the present day universe, AGN are your friend. And then finally, so hopefully a point that you'll take away from this is that AGN are not simply disks of gas that flicker, right? There are lots of things in and around AGN, and they can perturb the AGN, as I'll sort of point out, and their perturbations are potentially detectable with LSSTs, lots of exciting stuff we can do. But I'll, again, come back to this. I'll explain what's going on here later. Okay. So, and again, sort of before we get into what's going on, if you sort of read the AGN literature, you see this sort of zoo of acronyms. You see, all of these terms. You may have seen some of these: quasars, blazars, Seyferts, QS. Like it keeps going, and it's wavelength dependent, right? So lots of sort of AGN in the zoo, lots of classifications, but it's fine. Okay, for our purposes, all that really matters is there a disk? Is there a jet? And what angle are we looking at? That's it. Okay, so that's kind of what we're sort of going to focus on today. And today's simplifying assumptions. I'm going to assume, yes, there's a disk. Is there a jet? Kind of doesn't matter. Sorry, can I move the little zoom thing there? We're looking at this thing face on. It should say face on in there. Okay. All right. So, AGN luminosity. Okay, so let's talk about this. So here's an AGN, 3C273. What do you notice? So again, talk to the person next to you. Like, what do you see? What can you infer?
You think that blue
It's just what do you see as that?
No, like it looks like a ribbon that's going with it.
Yeah. They're both UV optical.
Yeah.
The bottom one is coronagraph that blocks the central light. You see on the top one, the central light has the diffraction spike. The X. The bottom one blocks. So it's
Oh yeah. Doesn't exactly like
it looks like it's I don't understand. Well, blue usually means stars, star formation, and then the red, you would think one would be half center, but the red is all direction.
I'm assuming it's
It's
I just like study it, make it famous.
Yeah.
We're not looking at it top down.
No, but it also seems like if we, if we look at that jet, the AGN doesn't look cancer as a direction. Yeah. If I were a better scientist,
this is red, yeah.
There's
Dust is full red and
Oh, yeah.
So, what do you see? There was a lot of talking again. You jump shy. Right, yeah.
Seems like there's a jet.
Seems like there's a jet. Yep, this thing sticking out this way. Yeah, you can also see it in this image. What else?
It's like a really, really like bright center, so you have to correct for that, otherwise the image is just really oversaturated.
Yeah, so check out the diffraction spikes on this thing, right? This looks like it's a really bright star that just sort of, photobombed your precious HST image, right? And just sits right on top of your source that you're interested in looking at. Yeah, so it looks like a star. It's a quasi-star, right? Anything else?
the jet kind of looks upturned at the start bottom, which.
So here and here, there's some sort of weird stuff going on here and here. Yeah, it looks pretty straight-ish. I mean, there's kinks and stuff in between, but yeah, there's little sort of things going on. Okay, so broadly, right, we've got this very bright star-like looking thing. This optical emission is first observed in 1887, right? And people thought it was a star. In 1963, in the third Cambridge catalogue, 3C27, object number 3C273, this became it was a radio source. And people looked at the spectrum of this star, and they realized, wait a minute, that isn't a star. And quasars were born. So the important thing about this is if you block out the light from this, two things. First, it's coming from the center of the galaxy. Second, this thing is outshining the entire galaxy, right? So if you want to sort of do an order of magnitude, you could say, okay, say there's 100 billion stars. This thing is shining at about 10 to the 45 ergs per second, right? So there's a quasar shining at about 10 to the 45 ergs per second. So in sort of the AGN field, one thing that a scale that we find that's really useful to express these insane luminosities is the Eddington luminosity scale. All you're doing there is you're doing something sort of analogous to hydrostatic equilibrium. You're essentially balancing two accelerations, one inwards due to gravity and the other outwards due to radiation pressure. And if you do that, is there any way of moving this this thing down here, Gishle?
Yeah, I also couldn't figure it out yesterday.
Is that that's a thing, is it? So the units here are in mass in terms of 10 to the 8 solar masses. So do I just have to explain what's underneath the black box?
No, it's hosted by the folks who are recording the ABD.
Okay, so they need to do it.
Yes, let me ask.
Yeah.
So on the first line, I guess it's so this order 10 to 11 L star comes from, you said the fact there's like 100 billion stars.
Yeah.
So
Ish.
isn't there any like extra luminosity from the accretion?
Well, we haven't talked about what's causing the luminosity, but we're saying that the thing that is coming from the center of this galaxy, whatever it is bright enough to outshine, 100 million stars. Therefore, solar luminosity is 4 by 10 to the 33 ergs per second times 100 million, you get something like this, 10 to the 45 ergs. Perfect, thank you. So this is a really useful scaling. You'll see this in the AGN literature. AGN will often be talked about in terms of their luminosity as a fraction of Eddington, right? And so, this is the sort of number that you want to bear in mind. Okay.
How do you do that when the black hole mass isn't very well constrained?
Yes. Yeah, that's true. You express your uncertainties, right? Yeah, and you try and find ways of getting at the black hole mass. I'll talk about that.
Also, don't worry, sometimes the bolometric luminosity is also not very well constrained.
Also true, yes. So in terms of the stuff that we're going to be talking about, AGN with disks. So this is the nearest and dearest quasar to us, redshift about 0.16. It's at about 0.2 of the Eddington ratio for its mass. Quasars are typically in the range of 10% to about Eddington in terms of their brightness. Seyferts, this other type of galactic nuclei that essentially we're talking about today, go from about 1% upwards towards Eddington. Okay, so then where does all the luminosity come from? Essentially, this whole thing is powered by the loss of potential energy in the deep potential well, right? So as you lose gravitational potential energy, you can figure out the energy that's lost. The rate of loss of that over time gives you an accretion rate, an m dot. And so effectively, mass is slumping inwards per unit time. If you say that that results in a sort of disky flow, then you can turn the emission from that disky flow into a series of annuli, each with its own temperature. And you can say, okay, so sigma AT to the fourth, here is how the temperature of this disky flow should scale roughly. Essentially, it depends on m dot, and it depends on how far away you are from the central mass, okay? So basically, the hotter, so the more stuff you start sort of jamming down the supermassive black hole, the hotter things you're going to get, and the closer you get to the supermassive black hole, the hotter things you're going to get. Okay. So, if you imagine sort of co-adding a bunch of black body annuli, you'll end up with some sort of spectral bump. And so the continuum that you're looking at should form some sort of bump from the disky flow that you think is causing this luminosity. What people generally in the field, you'll see this in AGN papers all the time, people calculate the luminosity directly in terms of the accretion rate, in terms of m dot. And so often you'll see it parameterized as eta m dot c squared. And eta is an efficiency factor. I'm not going to get into it, but effectively it's the efficiency of converting potential energy into radiation, right? So this is a quick and dirty way. If you think you know the luminosity, then you can figure out how much mass is falling in. So let's go back to that scaling that we had, this Eddington ratio. So if we say that this is the Eddington luminosity, then the equivalent Eddington rate is 2 suns per year around a 10 to the 8 solar mass SMBH. This quasar has a mass of about 10 to the 9 solar masses. And so the accretion rate here, the Eddington rate here would be 20 suns per year worth of gas, right? So these things are chowing down, right? They're really feeding. Because this is actually accreting at about 0.2 Eddington, it's eating maybe 4 suns worth of gas per year, right? And so if you think about it, over a mega year of operation, this thing would eat 4 million solar masses worth of gas, or the equivalent of the mass of the supermassive black hole in our own galaxy, in mass, in gas. That's how much this thing is eating. Okay. Okay. So as the sort of gas falls in, it's liberating more and more potential energy. The disk that's forming from this swirling flow is getting hotter. There's some sort of inner edge to the disk. It's known as the innermost stable circular orbit, typically the ISCO. And, you know, essentially it's going to end up pretty close to the supermassive black hole. For a non-spinning black hole, Schwarzschild black hole, the inner disk is going to stop somewhere around 6 gravitational radii. Gravitational radius is this, so about half the Schwarzschild radius. So this is 3 Schwarzschild radii. So you're getting really close, like if the supermassive black hole is this big, it just stops here, right? So you're getting in really close to the actual supermassive black hole. If your supermassive black hole is spinning very fast, prograde, you can get really close to the event horizon. And if it's spinning retrograde compared to the gas flow, the gas doesn't quite get as far before it starts plunging in. Okay. So if you go back to the temperature estimator that I had up earlier, and you plug in sort of the innermost disk value and rearrange, you end up with this thing right here. So essentially the temperature of that innermost disk depends on where you put the innermost disk, right? It depends on the accretion rate to the quarter power, and it depends on the mass of the supermassive black hole to the -1/4, right? There's a factor of 1 over m in here. M dot is proportional to m, or g is proportional to m. So you've got m squared under here, m up here. So a factor of 1 over m in here. That's where this comes from, right? So we've got an expression for the temperature that we expect close in to this supermassive black hole. Okay, so just taking this, again, I'll give you 2 minutes. What would this tell you about the temperature at the ISCO, at this innermost edge, if we suddenly change our supermassive black hole in the center of a galaxy to something in stellar mass? What would we get? So I'll give you 2 minutes. Again, you can talk to the person next to you. What sort of temperature do you think you would get? So keep this and this the same. Make this at a stellar mass. What are you going to get?
Yeah, yeah. It's like 1.0. Yeah. And then over time. Yeah. Our ISCO would change, so.
Let's keep our ISCO the same. So keep this the same, keep that the same, just change that. What's going to happen?
So let's say. Yeah, yeah. That's true, yeah. Our ISCO. Okay. The ratio between the ISCO and the gravitational radius might be similar.
Yeah, so.
Yeah, so our ISCO gravitational radius. Also the galactic stellar mass, I think it's 2 or 3. Okay, so order 1. Yeah.
So does it not? There's still some, like, in the tree version.
There's silence. So do we have any number? Like, does anyone want to give me a rough number? Like, okay, so let me rephrase it. Is the temperature going to go up or is it going to go down? Up, right? M to the minus 1/4. So I'm not saying there are black holes with 1 stellar mass. LIGO's yet to detect any, but essentially, if you drop this by 8 orders of magnitude, so 10 to the minus 8 to the minus 1/4, right? So you'll increase your temperature by a factor of about 100. That is why the black holes in our own galaxy that we observe, the stellar mass black holes, are X-ray binaries, right? This temperature close in emits X-rays, right? Okay, that was just a sidebar.
We have a question.
Yes.
Yeah, I was wondering, what about the Eddington rate? Doesn't the accretion rate change if this massive black hole is different?
So all we did here was we said, let's keep the Eddington rate the same. Let's keep this the same. Just change the mass. What happens? Temperature is going to go up. Right. Okay, AGN spectra. Again, you get to talk to each other for a couple of minutes. So here is the AGN, the broadband AGN spectrum of this thing. What do you notice?
I know it's a little like. Right.
I'm not familiar with the.
It's like around.
Frequency, yeah.
Very roughly. Yeah.
Means it can't be a black hole.
No.
Yeah.
Yeah, There might be another if you believe one of the spots of like 10 to 12.
Sometimes it's below that.
So therefore it's correct.
Yeah, like that's.
The triangles are rose line.
But, so I think.
So the triangle is the middle of X-ray. Well, so the left.
Yeah.
I can't find Kim.
No, me neither. But I'm just seeing.
Yeah.
Right. Then it also has.
Yeah.
Oh, Mauna Kea, I
So,
see Mauna Kea also. The visual is like from 10 to 1.
And then it's thermal. Not thermal, it's the power law.
Yeah, at the high, at the non-high X-ray.
This triangle? The black triangle is X-ray.
Like, all the way across.
Yeah.
Yeah.
From the internet. The internet. Yeah. Where's Monica?
Maybe.
What is radio?
I mean, the.
So right, that means 10 to the 15.
Okay.
Yeah. So it's a pretty big.
So I'm going, they call it terminal, meaning they kick you out.
And then
Some people go on.
It's really a.
Okay.
So, what do we got? What do you notice here? There was a lot of talking. Come on, like you gotta have some. Yeah.
Black body and optical.
I mean, so if this thing was a star, then you would expect a black body sort of that's in the optical. So optical is about here. You'd expect a, a narrow right here. If it's just a black body at a single temperature, right? Yeah, like
Non-thermal X-ray and radio.
Hmm?
Non-thermal X-ray and radio.
yep, right here and here. Yep. Where do we think that might be coming from?
Out close.
Okay. Anything else?
It's very bright in the ultraviolet.
It's really bright in the ultraviolet, and we're gonna come back to that. Yes, super bright in the ultraviolet.
Also, on a basic level, it's bright at almost all frequencies.
Yes, so check it out, right? It's really bright across, every telescope you point at this thing is gonna get something, right? You're gonna get infrared, you're gonna get optical, you're gonna get UV, you're gonna get X-rays, you're gonna get gamma rays, right? You've got sort of, what is that, 15 orders of magnitude in energy over which you can look at this thing and you will get something, right? But there's also sort of like bumps, right? There's a nice big bump right here, there's a bump here, there's a bump there. So we had our temperature scale here. Which bit of the spectrum do we think this sort of hot inner disk is responsible for? Again, you can talk to the person next to you. You can quickly do a calculation or Google search.
Really hot in this, and then progressively basically start with something that's very UV bright, and then get to things that are progressively less UV bright. Yeah, it's UV, right? is infrared lit.
Actually, now that I said it out
Oh,
loud,
yeah.
it should have been.
Yeah. Okay. Yeah.
But it could be, that's.
Yeah.
That was just more.
What wavelength is that temperature?
I still think that the
Oh.
big peak from IUE is probably from the thermal emission. Like all the
So, who thinks, hands up those of you who think that this temperature is associated with this peak? Okay. Hands up those of you who think that that temperature is associated with this peak. Hands up those of you who think this temperature is associated with this peak. Excellent, yes, right. So these features are often called by AGN folks the big blue bump, right? So this is if you want to fit this with models of annuli at different black bodies, go into sort of UV sort of producing regions, you'll end up with something that can kind of fit these features in quasar spectra, right? Depending on your choices of parameters. But what about these other bumps, right? So we had this big sort of X-ray and gamma ray bump. We've got a sort of infrared bump right here. We've got the iris points right here. What's all that about? So if you take a spectrum of this source in this region, in the infrared, you'll see dust emission lines. So immediately you can say, okay, well, dust is very fragile, right? It's this complicated thing that's broken apart at high temperatures, right? So we can use the luminosity of the AGN to figure out roughly where the dust would sublimate, or essentially where this dust must live in order to survive, to see it in this spectrum, right? And so if you do that, you get something on the order of parsec scales if you assume that dust is blown apart at sort of about 1,000 Kelvin, right? So in AGN, often you'll see this big infrared bump next to the blue UV bump over here. So the disk is producing this, and some dusty stuff that's removed from the disk, that's further away than the disk is producing your infrared bump, right? So it's physically separate, and that'll have some implications. So most people think that essentially this is a fuel source at sort of larger scales for the disk. Essentially, if you get some instabilities in your big dusty sort of reservoir, low angular momentum gas can come in and accrete onto the supermassive black hole, either powering the disk or starting a new disk, or adding to a disk that's already there. So because this is physically separate from this sort of disk that goes all the way down to the supermassive black hole, if a flare happens close to the supermassive black hole for whatever reason, what that means is you expect there to be a lag before the infrared producing region responds to that flare, right? And that lag is going to be, maybe a couple of years. So often in AGN, if you get multi-band spectra, you see a big optical or UV flare, you'll notice in the infrared, a couple of years later, boom, it pops up because it just saw what happened a couple of years ago, because these things are separate. And again, lags are important because they tell you about the distribution of material in AGN. And Amy is going to spend a bunch of time this afternoon talking about that. Yeah, so this stuff is cool, right? The dust has to survive. That means it's going to be puffy, right? It's going to tend to be volume filling. But if it's volume filling, that means it can block your view of the disk. So it's an obscurer, right? So type 1 AGN, you'll often see in the literature, these are AGN that are face on, where you can see down towards the supermassive black hole, you can see the disk. And the fuel source is presumably out here as a big donut. But if I turn it so that it's edge on, that dusty obscurer is going to block your view of the inner disk. And so type 2 AGN are obscured AGN, right? So in X-rays and gamma rays, so for this particular source, most of this is coming from the jet. You know, jets, I could spend an entire lecture just on jets. I'm not going to. All I'm going to say is, you know, jets we think are probably powered by a mechanism called Blanford's-Nyack. We're extracting spin energy from the supermassive black hole. So essentially you need gas, supermassive black hole spin, and magnetic fields. That's all you need to know. Again, the jet, as you saw in that image of the quasar, was physically separate from the disk, right? So again, these physically separate regions in AGN are important for producing these different parts of the spectrum. In AGN that don't have jets, you know, this is an X-ray bright safer one. AGN, we pick up X-rays from these sources, and you see this sort of flicker. And based on the sort of timescale of the flicker, how big do you think, in terms of light seconds, must the region producing this be? If you look at this, right? So assume the flicker is due to the changes across a coherent thing of a size, right? How big do you think that thing might be? I'll just give you 2 minutes. Again, talk to the person next to you. Producing something that looks like this.
Yeah. Oh, okay. I don't know. Oh, you said the light travel. Yeah. And so that's why. Yeah.
So what do we reckon? How big is the thing that's roughly producing this stuff, do you think?
It looks like the flicker is at maybe like 10 to the 4-ish seconds. So in terms of light seconds, that's like 28 U.
Exactly. Yeah, that's right. So ballpark, you can see, right? You can see that, you know, this is 10 to the 5, this is 2 by 10 to the 4. Like the variation is less than that, so say roughly half. So about 10 to the 4 seconds. Yeah. That's 3 hours. So 3 light hours, right? So that's about 28 U. So that's out to Saturn, right? So the area in this AGN, right, in the center of this galaxy that's producing this X-rays, essentially is coming mostly from a region that's smaller than the distance between the Sun and Saturn, roughly, right? Side note, sometimes those can get eclipsed. This is the first eclipse of an AGN observed in any wave band. You can ask me about it later. Okay, so where are the X-rays coming from? Well, we have this sort of hot inner disk, right? It's producing all these UV photons, but the gas is going to be hot. There's going to be some free electrons produced. There's magnetic fields around, right? So I have this sophisticated cartoon here with lots of fast electrons zipping around, and I've got some UV being produced by the disk. What's going to happen when a UV photon hits one of these very fast electrons? So again, I'll give you a couple of minutes. What do you think is going to happen?
Yeah.
Well, what do you mean? If you just could describe it in words, but you have to like get relatively it happens.
Right? Oh, the actual sound. Oh, you're right. Okay, got it.
I don't remember which one is which. Yeah.
Oh,
You said something.
In the internet.
So what do we think is going to happen?
Inverse Compton scattering.
Yeah, exactly, right? So you have this hot disk, you kind of boil off the electrons, they're bouncing around, they're really fast, moving around, but you're also producing this really intense, this incredibly luminous source of UV photons. The UV photons are rising through this sea of fast-moving electrons. You know, one of the UV photons hits a fast-moving electron. The electron gives its energy to the photon, and you get X-rays. So this is where those X-rays are coming from. It's this inverse Compton process. You're reprocessing disk radiation, turning it into X-rays, right? A jet will complicate this because the jet can also act as a source of X-rays, but I'm going to stay away from that. Okay, so we talked a little bit about sort of the spectra and the luminosity. Let's get into like how we think disks work. Okay, so AKA, how does the gas actually end up on the supermassive black hole? So we think it's due to a process called magnetorotational instability, known as MRI. And so I want you to just think for a moment about what should happen in this picture. So let's imagine the supermassive black hole is over here. We're in a differentially rotating disk, which means that packet 1 is orbiting faster than packet 2. Packet 1 is also hotter than packet 2, right? But imagine that there's a magnetic field line connecting these two, right? A sort of spring. What do you think is going to happen here as we let this system evolve? Okay, and again, take a couple of minutes, talk to the person next to you. What do you think is going to happen?
The inner, yeah, so rotating faster.
Or is each one a pole?
Oh, no, we should probably listen to the rest
What is gas going around like this? Magnetic charge.
Yeah, right. It's like a little packet.
Okay, cool.
Yeah, that's fair.
Do you remember how rotating ionized gas creates the magnetic field?
Very strong. Right, if it's magnetic, that's less than 1. If it's gas pressure, it's greater than 1.
And then the inner one will lose any stable orbit it has that's lost velocity.
So what do we think is going to happen in this cartoon? Yeah.
So it's going to be pulled closer together and velocity, which will push them more out.
Okay. All right. So something's going to happen for sure. Anyone else? What do you think is going to happen?
Angular momentum transfer outwards.
Angular momentum transfer. So if you're conserving angular momentum, what should happen here? Well, so let's stick with the cartoon picture right here. Anyone else? What do you think is going to happen to?
In like a really basic sense,
Yep.
is the like block one or the
Yep.
block going to experience a different gravitational force to the red block, and then because they're like linked, that's then going to impact the outer part of the disk as well?
Yes. So fundamentally, you're connecting two differentially rotating regions. That's right. I think I saw a question. Yeah.
Yeah, I think the energy or like the second block will start to like move maybe a little faster, or like essentially angular momentum gets transferred from the out to the second one, so the inside one moves further.
Okay. Yeah. So what's going to happen is essentially you're going to stretch the spring, and the restoring force in the spring wants to take angular momentum, wants to slow this thing down and send it this way, and it wants to speed this thing up. Right? That's sort of essentially qualitatively how you want to think about this. But what that means is if you slow down that parcel of gas at 1, it's going to start to move further in. And if you speed this thing up, it's going to want to move further out, right? So you can see that, well, if you just move this one in, then it's going to keep doing the same thing, and this is going to run away. This is unstable, right? And so imagine all of the parcels of gas in all of the annuli in your disk that you've constructed, connected randomly by magnetic field lines. This is going to be a mess, right? But you can also see that it means that you get accretion onto the SMBH, but also you get angular momentum being pushed out, so gas is being pushed out, which can drive winds and outflows, right? Okay. So what does that mean for our picture of the disk? So essentially, we're losing angular momentum in this disky flow. It's kind of hotter in here. It's cooler out here. There's differential rotation, and it's going to be turbulent. And what I'm going to say before I get on to the next bit is this. So every single AGN disk model that you see is wrong, but they are all useful. All right, and I say that before I get into this. So we have this turbulent disky flow, and there is an entire class of AGN disk models called alpha disks. And these are thin disks, so they're geometrically thin, optically thick, so they're dense. You can't kind of see through them, but they are pretty thin. And we treat those with we treat the turbulence that we think comes from MRI as a viscosity with a parameter that we basically, essentially a dial that we return. In the limit of low alpha, very little material will move inwards to the supermassive black hole. Stuff will stay in Keplerian orbits. There's very little turbulence. And in the limit of large alpha, you'll drive a stronger flow inwards, right? So alpha disk models essentially parameterize the messy details of turbulence. And essentially all you really need to know is large alpha, high accretion, low alpha, low accretion. And it's a very simple parameterization. It's, wrong, but useful. So speaking of useful, let's get on to some timescales, because this is going to be relevant to some of the stuff you're going to be working on with Amy. So the very first place I would start is sort of anchor your timescale expectations with orbital timescales. So, just use Kepler here, and to sort of anchor your expectations at about 1,000 gravitational radii from a 10 to the 8 solar mass supermassive black hole, your orbital period is about 3 years, right? And it's going to scale as R to the 3/2. So timescales that are sort of shorter than this may involve orbits that are closer in than 10 to the 3 RG, for example, right? There's a bunch of timescales you can kind of figure out. If you're interested in the details, you can go to Stern et al. 2018. Essentially, you can, in alpha disks, parameterize various timescales for various processes. So how gas heats and cools, your thermal timescale, how a cooling or heating front propagates radially through the disk, and what those parameters it depends on are. So if we rescale to 100 gravitational radii, we're now at a 1-month orbital time around our 10 to the 8 solar mass black hole. Sort of thermal timescale for this choice of alpha in this disk with this level of turbulence, sort of year-ish timescales. The timescale on which a front travels through a disk that has an aspect ratio. So this is the height of the disk compared to the distance that it is from the supermassive black hole. So the aspect ratio, about 10%. In this example, it's about 20 years. And finally, sort of the important bit, the viscous timescale. So this is the timescale on which a parcel of gas with mass is going to move inwards in the disk. For these, rough parameters, it's at 100 RG. It's around a 10 to the 8 solar mass supermassive black hole. We've picked a value of alpha, saying that there's a given accretion rate, and the disk is sort of puffy-ish. It's not like razor thin. It takes 200 years for that gas in this disk to get onto the supermassive black hole. Okay, that's interesting. And here's a question for you. Again, take a couple of minutes, talk to the person next to you. Using our viscous timescale and using our parameterization, we scaled it to 100 gravitational radii in a disk around the supermassive black hole. Let's say that our disk extends to 10,000 gravitational radii. How long will it take that gas at 10,000 gravitational radii to be eaten on this timescale? Like, how long will our disk live? So again, don't worry about this term. Don't worry about this term. Don't worry about this term. You're only changing that. So again, talk to each other.
That's so fair. Yeah. Maybe the 3 halves is. Yeah, wait, 10 to the 2. To the 3 halves.
Yeah.
Sorry.
Yeah.
Times 2 divided by 2 is 2. Which is 1,000. So then 1,000 times throwing it. 150 for about 3 10 to the 6. There is? Okay.
200 divided by 1,000.
10 to the 6.
Because it's Earth.
Or at least for me, it's at least for me, it's I don't know. Which is so when I do
Oh, it was.
that's the problem. When I ask them how to do it, because I don't know how to do it. This may be what I so I think that's the and it's like
Surely I can do it.
yeah, no, totally.
So what do we think? How long is it going to take a disk with, these parameterized properties that goes out to 10,000 gravitational radii? So not 10 to the 2, but 10 to the 4 gravitational radii around this black hole. How long will it take before that gas is transported in this picture? What do we got?
200,000 years.
200,000 years. Right, so all we've done is we've changed 10 to the 2, 10 to the 4, 10 to the 2 times 3 over 2 is 10 cubed, so 1,000 times this, 200,000 years, 0.2 mega years. So this is a relatively short-lived AGN disk. If you think AGN disks live for a relatively short period of time, this is the sort of size scale that you're looking at with these approximate parameterizations. But you can see that basically, if you change the aspect ratio, if you make the disk less puffy and thinner, it's going to take a lot longer for that gas to flow its way to the supermassive black hole, right? Okay, so we have some timescales. Back to our favorite AGN 3C273. From top to bottom, here is an optical light curve. Here is a UV light curve. Here is an X-ray light curve. What do you notice about the timescales of variability here? What can you say? Again, I'll give you 2 minutes. Yeah, in case it's hard to see, right? That's 1980, that's 1985, that's 1990. So each pair of tick marks here is a year. Okay.
Oh, what time? About a year ago.
After all IR.
It's kind of hard.
That's the one that's supposed to have
So
So it's interesting that the optical is so much flatter during that period of high variability.
the one that kind of looks like that. Yeah. On the right, like the first one.
It looks like that big spiral spike
Around the time of that first
a bit of X-ray activity, and before the spike goes in there, maybe that figure spike but then again, the first big IR spike is ahead of the first big spike. And then there's not a commensurate IR spike after it, so it doesn't look like it's the first big spike. So, what do we got? What do we see here? So again, optical, UV, X-ray. What do you see? Like, what are the timescales that we're talking about? Yeah.
In all of the regimes, you have variability on timescales of months to years.
Yeah, so, you know, you can see the optical kind of burbles along. You know, there's maybe this sort of underlying like several year thing going on in the optical, but you get these like spikes on much shorter than year timescales, right? These are, you know, months, maybe even weeks, depending on the details. When you get to the UV, it seems a lot choppier, right? You can see these kind of spikes popping up. Then, now, part of that can be like how often you're observing the system, but it basically seems like the timescales are a lot shorter in the UV. Again, that's it's coming probably from a smaller region, typically, right? In the innermost disk. In the X-rays, spotty coverage, but when it changes pretty quickly. Again, on well sub-year timescales. Some of these lines are almost vertical, so there can be very rapid changes in the X-ray. There's a complicated source because you're not just talking about X-rays from the corona, this tiny region near the supermassive black hole. You're also talking about processes in the jet. That's a whole separate issue I'm not going to get into. But essentially, you could look at this optical plot and you could say, okay, the shortest timescale of variation is probably something like a week timescale. And so that means that the sort of region that you're talking about roughly on a light crossing time is probably about 1000 AU, right? So that's roughly where these variability processes are coming from. And this was, you know, an original argument when people started looking at these things. When they saw these short timescale variability, they sort of realized, oh, this radiation must be coming from a very small region. It can only really come from something like an accretion disk that's very efficient at liberating energy. Okay. Right. Yeah. So if you take a spectrum of the optical light coming from 3C273 and you put it into the source frame, you see, you know, there's a rising continuum towards the blue, right? 400 nanometers is here, right? So you're going from, you know, yellowish out to sort of greenish yellowish out to blue. Cut off here, your continuum is increasing towards the UV, right? Because we expect the hottest part of the disk is coming from in here. So we're looking at sort of this chunk of it. And we see these broad emission lines. And this is a sort of common feature in the quasar and Seyfert HEN in particular. This line right here, H beta, is a very, very popular line to use because it sits at a convenient wavelength for HEN that are in the local universe. So, you know, most optical telescopes can hit this and can get details in the line. The sort of the full width half max. So, you know, this width right here of half the maximum of the line. If you figure out the sort of the equivalent velocity for these lines, typically between like roughly 1,000 kilometers per second and maybe 10,000 kilometers per second, right? That turns out to be really useful. So one of the things that we notice about broad lines is that if we have a flare in the UV or in the disk, the broad lines don't immediately respond. They don't know about it. But if you wait, typically for a month or so, the broad lines pop. They'll respond to whatever just happened. So there's a lag between where the broad line clouds, these things producing these broad lines are, and the innermost regions of the disk. So again, we're talking about physically separate regions with a time lag between them. So this just shows you the lag in the H beta line as a function of the luminosity of the AGN. So sort of quasars are sort of out here, Seyferts are kind of in here. And this is for a sample of AGN, roughly, a month-ish is sort of a reasonable ballpark for the time lag in these systems. So you've got a series of clouds that we think are part of a sort of, you can visualize a sort of hurricane or tornado of material being blown off the disk, because you conserve angular momentum. As you drive all this stuff in, you must conserve angular momentum, so you're also driving material out. You're blowing a strong wind off your disk. The things that are producing these broad lines may be clumps in that outflowing material, so you can imagine this stuff sort of swirling, essentially spiraling outwards, but really slowly. So physically separate region from the disk. And this is really, really handy. So if we know that this stuff is sort of only slowly spiraling outwards, then we can treat it as more or less in a Keplerian orbit-ish. And so what we can say is we can measure the lag between a flare and the response of the lines. We know how far the line producing clouds are from the innermost disk, right? We can measure the width of the line, right? And so if we associate that with an orbital velocity at that distance, you can immediately figure out the mass of the supermassive black hole. So this is a really great way of constraining the mass of the central system. And this is essentially how we did it back in the day. So in this case, say the lag is a month. The broad lines take a month to respond to a flare. Their width is about 1,000 kilometers per second. Plug it in. Your black hole is about 6 million times the mass of the sun. Okay, cool. So we can use the broad line region to do lots of cool things. All right. Exciting things to search for.
Question.
Yes.
So in the Alsace Tierra, where there's basically no more spectroscopy for the number of things we're going to see, can I do that photometrically?
For things that are very interesting, and we'll get onto this, you'll want to get spectra for them. You can try, but for anything that I think you're so there are ways that it is less reliable. I'll say that if you do it photometrically, the gold standard would be measure the lag, get the spectrum, get the widths of the lines, and do it like that. But there are other ways that people use, but it's less reliable. Okay. Oh, yeah.
Let's see. I'll talk a little bit about using timing to do black hole masses. So.
Yay. Oh, perfect. Excellent. Good. Okay. So now the important bit, right? Exciting things to search for. Yeah. So if we put all of the stuff that we've discussed together, right? The luminosity, the spectra, the variability, you end up with a classic cartoon, right? There's supermassive black hole in the center. Great. We've got a disk in here that's producing all our, UV optical emission. We've got some clumpy stuff in an outflow. That's your broad line region. Cool. There's also narrow lines, which I haven't spent any time on. There's a sort of dusty donut on parsec scales that's producing your infrared emission. Maybe you have a jet, maybe you don't. Depends. About 10% of AGN have prominent jets. So you get this picture, but we're missing something in this picture. What are we missing? Stars. AGN disks are not just a collection of gas, right? So this is an image from the Gez group of the orbits of some of the stars close to our own supermassive black hole in our own galaxy, Sagittarius star. So you're tracking orbits, you can do all kinds of things. That's fantastic. What you can see is there's a swarm of stars, swarm of stars. Presumably those stars have died and left behind black holes. So you could also imagine things we can't see orbiting this thing, right? So you've got stars, stellar mass black holes, you've neutron stars, whatever, right? You've got everything in here. If you then throw a disk on top of this, then you're going to get some fireworks, right? These things are going to have to interact with the disk. Some of them will end up in the disk, and their behavior and their masses, spins, all kinds of interesting things will change, and sometimes they'll blow up. Okay, that's exciting. So typically in sort of galactic nuclei, you have a nuclear star cluster, right? So on the order of 1 million stars also live in this picture, right? In the central cubic parsec of our own galaxy, we expect on the order of 10,000, I'll say that again, 10,000 stellar mass black holes. The densest population of stellar mass black holes anywhere is in galactic nuclei, right? Mass segregation, infall of globular clusters, ongoing star formation means that there is a dense population of stuff in here. So potentially millions of objects interacting with this thing. And that is juicy, juicy territory for LSST. Okay? Okay. So if you have an object that's crossing an AGN disk, then you can figure out basically the temperature associated with the shock of the splash as it hits the disk, especially if it's traveling fast near the innermost part of the disk. It'll generate X-rays. And so there's this new sort of understanding. Itai probably talked about this with TDEs, right? The association between QPEs and TDEs, where essentially if you have a disk and something smacks through the disk, you get X-ray flaring, right? We're starting to see this particularly in AGN that are turning on. So new AGN that haven't been pumping out radiation for a long time, gas arrives in a nucleus, you're starting to disturb orbits of stars, things will plunge through the disk, you see stuff that looks like this. Fantastic. There are things in AGN disks, and this leads to a whole host of interesting things. So if you just think about black holes, stellar mass black holes in AGN disks, you can kind of imagine an AGN disk as not too dissimilar to models that you've seen of protoplanetary disks, where you have a star in the middle and you're trying to build up planets from the collisions between objects. Essentially, you can do the same thing in AGN, but with black holes. You can get little black holes to sort of migrate within the disk, find each other, merge, produce gravitational wave events, and have a whole host of different interactions. So this is a cartoon from Hiromichi Tagawa's paper in 2020. If you're interested in this stuff, myself and Savick just wrote a review on the LVK AGN channel, why you should care. So go there. More recently, last week, LIGO announced, LVK announced event GW 231123. That was an intermediate mass black hole merger, both with very high spins. If this is a hierarchical merger, so essentially if we think we understand massive stars, this was a hierarchical merger, it happened in an AGN. It didn't happen anywhere else. It was definitely an AGN event. And that tells you something about some of the processes that are going on in these disks. if you have a merger, a binary black hole merger in a AGN disk, the merger isn't happening in the dark. There is gas, there is fuel supply around the black holes. They're accreting. When they merge, they get kicked. They will drag some of the gas with them. Gas is magnetized. When you merge two stellar mass black holes together, you'll spin it up really fast. So you have the potential for forming a jet. So essentially, there's been a stack of work over the last 5 years in particular on how EM counterparts might emerge in AGN from binary black hole mergers. Essentially, it seems to come down to jets want to form in these events and simulations. The question is, can they persist? So that's a big open question in the field. Back in 2020, we saw a flare in an AGN very closely associated with the then most massive binary black hole merger, GW 190521. Is it associated with the merger? We don't know. It was a very rare event for this AGN. So who knows, right? But essentially, this is an ongoing industry that people are.
Can I ask a quick question?
Yeah, sure.
Did anyone look for an electromagnetic counterpart to the intermediate mass black hole merger?
To 231123. So LVK have only recently given chirp masses associated with events. So in O4C, you can now get the chirp mass associated with events. So you get an idea of the mass associated with a given event. So before that, we had to guess based on the rough data they were giving out. Our mass estimator for that event came on the low side. The sky area wasn't great, and so we didn't immediately follow it up. But I will tell you that on Slack, there are so many people looking for archival stuff, and people are trawling through. So if there was something that went bump, we'll be able to say something. But yeah. TDEs. So if you are interested in TDEs, you will love AGN. Don't throw them away. AGN are going to be a great source of TDEs. Why is that? When you bring in an AGN disk at the beginning, you're going to interact with the orbits of stars. You're going to scatter things. There's a whole bunch of interesting dynamics that's going to go on, and the rate of TDEs in AGN is going to be highest at AGN turnoff, orders of magnitude higher than the standard quiescent AGN, or sorry, standard quiescent TDE rate, which is 10 to the minus 4 per galactic nucleus per year. So you can get orders of magnitude higher than that. So what's going to happen? What would you expect to see? There's a cartoon here which basically says, okay, you can maybe scatter a star in, and you can maybe clear out some parts of the inner disk. You would get a very bright flare. The continuum level after the flare will drop to below the previous value of the continuum because you've just removed a chunk of the inner disk if the star comes in on a retrograde orbit. So essentially, if you kick a star in and it's moving backwards compared to the gas and you shred it, you cancel angular momentum and you clear out the inner disk, you drive a very rapid accretion event. It'll be very bright, and then you kill emission from the inner disk. So essentially, you'd expect something that looks kind of like this. For a prograde tidal disruption, it looks slightly different. There's some references here if you're interested, but I will show you this. So this is a paper in prep from Tehu Ryu. What he did was he took stars and threw them prograde and retrograde through an AGN disk and got them to disrupt close to the supermassive black hole. So essentially here we have a star that's coming in retrograde, so it's backwards compared to the gas flow. Here it's coming in the same direction as the gas flow prograde. And what you'll notice is as you come in retrograde, you clear out that inner disk. Right? So essentially, you're just driving all this sort of disk gas away, which means that your AGN continuum is going to change, right? You're just nuking that inner disk. So you should be able to see this. This is a top-down view. This is an edge-on view. This is magnetic field behavior. But retrograde TDs should stand out in AGN. And I think Suvi is going to be talking about this, but there are a few examples in the literature of what look like really big spikes in luminosity. If you integrate the energy under these things, they can't come from very many things. They have an energy that you might associate with something like TDE, and they seem to impact the disk afterwards. So it looks like we're starting to see TDEs in AGN at a high rate, particularly in AGN that are turning on. Sometimes we see interesting features, potentially partial tidal disruptions and repeaters. So there's a whole sort of space that's opening up that is ripe for enthusiastic graduate students to dive into and play with. Sort of, things are moving fast. There are some very luminous flares that people are detecting in AGN. The latest thing is extreme nuclear transients. We think these are massive stars being disrupted in AGN. So for your standard TDEs, you're talking about disrupting your common or garden 0.5 to 2 solar mass star, throw it at the two-body interaction, kick it in, it gets disrupted. Yay. These guys are more like 10 solar masses that you're throwing in, you're shredding, and it's impacting the disk, and you get these explosive kind of events in response. The disk seems to change dramatically. There's a whole bunch of timescales and intensities you can play with, but essentially by figuring out the energy associated with these things, this isn't disk gas stuff. This is something coming in on a short time scale, hammering the disk, right? So these are things you can search for with LSST. Stars. All I'm going to say about stars in AGN, they are not normal. Matteo is going to be giving, I think, a class or a lecture next week. So ask him about stars in AGN. They are not normal. They don't behave normally. You expect them to pull gas from the disk and grow in mass. So again, these are a great source of these massive star TDEs that we think might be going on in AGN, these rapid changes. Some of those stars, they're going to blow up. They'll be supernova. Maybe they'll be muffled. Maybe they'll be bright, Okay. So big open questions for you to tackle. How big are AGN disks? We don't know the answer to that. How long do they live? We don't know the answer to that. What populations live in them? We don't know the answer to that. And how are AGN born? How did they die? We don't know the answer to that. But sort of in more detail, what we're interested in is that physical layout of where things are. So where's the disk? Where's the infrared producing stuff? Where's the jet? Where's the broadline region? Can we map these things? And how do they interplay based on time lags, for example, right? If you can tackle this question, how long AGN live, then you're tackling fundamentally how efficient they can be at providing that feedback that we said is really important for sculpting a galaxy, right? If it doesn't last that long, it can't provide that much feedback, right? What populations live in them? If you're interested in supermassive binary black hole mergers, if you're interested in little things, if you want gamma ray bursts in AGN, there's so many things you can play with here. And this final question, how does fueling work? Okay, finally, clues to look for in LSST. So this is what you should be doing, right? Hopefully I've convinced you that AGN are going to be the site of some really interesting things and that you should play with timescales and look for certain changes. So look for big changes. Look for things like periodicity and quasi-periodicity. That's going to be an interesting thing that's going to tell you something. Look for AGN that have turned on recently. Sidebar, if you're interested in this, you can figure stuff out from narrow forbidden lines. And then, look for AGN that are responding in response to multi-wavelength sort of gravitational wave things. So on the sudden changes in light curves, think about timescales, think about energy. One very important thing in LSST that you should be wary of is if your AGN is a strongly jetted one, you may get sudden changes in your light curve. People aren't going to believe, the result that you present if it's a blazar, right? They can change very rapidly. Periodicity, quasi-periodicity, you can test a whole bunch of stuff. I didn't have time to talk about warp disks, precessing disks. That's a whole thing. AGN turning on recently are an excellent playground for TDEs in particular, massive TDEs. And then anytime Swift says something interesting in tandem with, say, LVK or PTA or ELISA, this is the future. Okay, that's it.
Right, we have time for 1 or 2 questions.
What do you think our prospects are for being able to distinguish just the generic AGN players and things like TDs and mergers, and what would be best, what are ideas in going about that path?
Right, so Amy is going to talk about sort of more generic variability within AGN this afternoon. The thing that you want to pay attention to are huge sudden changes in your light curve. So if you see a strong flare, if you know the luminosity of the AGN, figure out the integrated energy. And if your integrated energy is north of 10 to the 50 ergs, there's very few things that can do that. Something big happened, and you can then play with what the system is doing. So the very first thing I would do is look for big obvious things and jump on them and see what's going on. But make sure there isn't a jet there.
You said a big open question is thinking about populations in the disk. Is anybody modeling the populations in the disk?
Yes, including you.
Yeah.
You mentioned the X-ray flares from AGN that are just turned on with stars embedded in their disks. Do those X-ray flares differ from the QPEs that we see after TDEs in ways that reflect what we expect to be the differences in the disks and their structures?
Yeah, so essentially, I guess, right, a TDE, so a classic TDE is kind of a micro AGN, right? You've got a little disk and it's accreting and it's doing its thing, right? AGN disks are just a lot bigger. So you've got a bigger surface area. So, something that's crossing that may have a different orbital period. Typically, the sort of things that we're starting to see are sort of longer orbital periods. So you're punching through a bigger disk. So there's a longer lag between the sort of QPs that you see in ETI's QPs, right? Yeah, and then, you can play with, well, okay, what sort of density would I expect if I'm throwing a star at a disk and I'm doing that at 10,000 kilometers a second? What do I expect, right? How long should that flare last? How is that a function of the density of the disk that I'm punching through? So again, something to play with, turn some knobs, see what you get, rule out maybe some low density cases, tell us something interesting about the density that you need to punch through, right?
Okay, so we have Suvi back again to tell us about the observational manifestations of all this exotica we heard of in the morning, including how LSST would be able to find these things both for the generic AGN variability and these extreme events that we heard of. So, go ahead.
Great. Well, historically, when there have been transient conferences, we don't normally talk about AGN, but it turns out that, as we just heard this morning, we expect AGN to be the hosts of transient accretion events. And indeed, now we see that AGN can undergo dramatic changes that really put them in the category of transient phenomena. So a lot of the work I'm going to be talking about again today is going to be using these wonderful optical time domain surveys. Again, this is an example of the ZTF imaging that we use and difference imaging, but I'll also be talking about a survey called Pan-STARRS, which is a predecessor to ZTF, which was the Pan-STARRS telescope in Maui, and also was really valuable for studying variability in AGN. Okay, so how do we find supermassive black holes in the universe? Well, we heard several examples this morning. We can use spectroscopy to see the characteristic blue continuum and broad emission lines associated with AGN. We can look at multi-wavelength data in the X-ray and radio and look for the evidence of relativistic jets that must be powered by an accreting supermassive black hole. For dormant black holes, we can actually see the gravitational influence of the central supermassive black holes on stars and gas in the very center of the galaxy, and actually infer the presence of a black hole, not from the radiation it outputs, but from simply its gravitational pull in the center of the galaxy. We can also use, we heard a lot about the big blue bump, this peak in the UV that we see from what we think is the accretion disk in these events. So that produces an ultraviolet excess that you can pick up by using just optical colors. You can select quasars from their colors, which are distinct from stars. But today I'm going to be focusing more on the aspects of AGN that we see in the time domain. So yesterday I told you all about what we're learning from observations of what we call tidal disruption events, where we think that the large amplitude flare of radiation that we see from a quiescent galaxy is in fact due to the disruption and accretion of an individual star. But we also know by looking at AGN, one of their hallmark characteristics, especially if they're unobscured. So you're this dusty torus we heard about is not actually blocking your view of the central engine. But for unobscured AGN, one of their hallmarks is stochastic variability on multiple timescales. So in my lecture today, I'm going to be talking a little bit about the variability behavior of so-called normal AGN. So what are some of the characteristic variability properties of AGN? Then I'm going to show how it's been argued that we can actually use the characteristic timescales of this variability to actually measure the black hole masses in AGN. This is something that would then be quite powerful for a time domain survey like LSST. Then I'm going to introduce this extreme class of objects called changing look AGN. And then someone in the room can try to explain to us what is causing their behavior. We're not sure yet. Then I have 3 cases here that I think are fun examples of what you can do with AGN variability and completely ignore the physics of what's actually driving the variability, but simply use it as a way to pinpoint accreting black holes in galaxies. So I'm going to show you how using ZTF and WISE, we've used variability to identify candidate intermediate mass black holes in dwarf galaxies. I'll show you how we've used variability to pinpoint off nuclear AGN that are from runaway black holes. And then I'll also show you how we've been trying to use variability to find candidate binary supermassive black holes. So all of these science cases are going to be even more relevant in the Rubin era. Yeah, so just a reminder to you of this incredible increase in survey volume that we're going to get from Rubin. That's really going to open up the study of faint and rare objects, and it's going to be really powerful for increasing our populations of transients as well as variable AGN. So again, we see black holes, or they reveal themselves in the centers of galaxies, or sometimes not in the centers, when they flicker and flare as they feed on gas and stars. And we can actually use variability alone actually to identify quasars. So I said that you can select them based on color, but it turns out that if you color code this map here by variability, the quasars also really stand out not only in color space, but also by just the amplitude of their variability. You can see that there are some other stellar variables that show up here, for example, R Lyrae. However, you can use the stochastic nature of the quasar variability in comparison to more periodic variability seen in stellar variables to actually distinguish them from stars. And so it's been shown to just by using the light curve alone and no other attributes like the color of the sources or even the spectrum, you can distinguish quasars from stars. So maybe this is something you'd want to do with Rubin, which is use the beautiful multi-band light curves and just identify all the quasars simply from their variability characteristics. I will note that here we've also they've also selected point sources. So here we're talking about quasars where they really outshine their host galaxy light. So they're actually point sources. So all the light is coming from the accreting black hole. So a generic property of quasars that all of you should be aware of is that if you look at the amplitude of the variability as a function of wavelength, so this is was done back in 2003 using 25,000 quasars from the Sloan survey, you can see that there's a very strong trend that as you get to shorter wavelengths, so approaching the rest frame UV, you have larger amplitudes of variability. So that's what we call bluer when brighter. Yes.
I feel like I should know this.
Do you want to use a microphone? Yeah.
I feel like I should know this, but are all AGN quasars?
No. So quasar, the term, I think came from the radio, which is where they discovered, these quasi point-like sources. AGN, so typically the way we use the word quasar now is thinking of AGN that are so luminous that they are point sources and they outshine their host galaxy. AGN is a catch-all term for all types of accreting supermassive black holes, so Seyfert galaxies, blazars, quasars, things. But it can also refer to sources where you actually see the host galaxy as well. So Barry introduced these different potential timescales in an AGN. And this is a model for what variability would look like if the important timescale were the light crossing time versus the orbital timescale versus the thermal timescale in an AGN. And so you see that the variability is stochastic, but it does have some predictable behaviors in terms of the amount of variability on the different timescales. And it's been, there's been a framework developed to explain the observed variability in AGN to sort of capture the properties of the stochastic variability that we see. And they've come up with this something called the damp random walk, which shown here is a structure function which tells you the amount of variability as a function of the time scale. So if you look at all of the points separated, for example, at 1 year, I think this is in I don't know what this unit is here. But let's say it's 1 year. You look at all the variability of points separated by 1 year and you average them. That gives you sort of the amount of variability on that time scale versus 10 years versus 0.1 years, for example. So this damp random walk has the attribute that you see variability on all time scales, but in particular, it increases as you go to longer time scales. No, is this time? Yeah, does that make sense? No, it would make sense if it was shorter time scales. So this is 1/tau. Okay, so the variability increases as you get to shorter time scales until there's a cutoff, and there's a minimum time scale below which you don't see any variability. So for example, one way to think about this is if you had a disk with an innermost radius and you have some orbital time scale associated with that radius, then because the disk cutoffs and you don't have any emission within the ISCO, there might be some minimum time scale below which you don't see any more variability because of the finite size of your disk. So the way they've been able to model AGN light curves is using this power law, this sort of red noise, which then has a turnover. And so you have this characteristic time scale tau, which I'll talk about. And we can measure that in the light curves. And then what we try to do is explain, what could that be tracing? And for example, they've taken this damp random walk formalism and fit it to observed light curves of AGN in the optical, shown in the black points, and in the X-ray, shown in the red points. And so they've measured the power, the amount of variability as a function of time scale, and then looked at where that turned over. And that turnover time scale is shown here in days. And you can see that if you look at the inferred black hole masses for these systems, it does look like the turnover time scale scales with the black hole mass. Now, with the X-ray variability, it actually scales exactly closely to what you'd expect for the innermost radius of the accreting disk, so this ISCO. So that actually makes you think that, oh, if you have a really good X-ray light curve and you can measure its power spectral density and measure that turnover time scale, then you can infer, based on that minimum time, if you convert that to an orbital time scale, you can infer the black hole mass because it's in units of Schwarzschild radii. So that's exciting. And then the optical variability also has a trend with black hole mass, but it's not as steep. And so it may be tracing another time scale that depends on black hole mass. And I think in this paper, they argue that it may be related to the thermal time scale, which you heard about earlier. So basically, this is an argument that if you have a really good light curve of an AGN, you could use it to measure the black hole mass using this, the structure function or the power spectral density distribution. So this is a great test in that I talked a little bit yesterday about interest in lower mass black holes. And we're very interested in actually finding intermediate mass black holes because they may be a key to how supermassive black holes actually form in the early universe. And so here's an example of one of the few known cases of a dwarf galaxy with a AGN. So it has broad lines, just like you heard before, but it's a very small galaxy. And so you expect it to have a relatively small black hole. So to test this, let's test this timing idea, where instead of using the virial method, which is using the width of the broad lines and the continuum luminosity, which I'll talk about more in a second, let's actually just use the light curve. Now, to get the light curve that you need to measure black hole mass in a lower mass galaxy, I just want to look here. Like, let's say you had a black hole mass of 10 to the 5th solar masses. You're looking at time scales that are less than a day. Okay, so Rubin, not going to do a great job with that. Maybe someone has done some fancy simulations so you can, but in general, you really need a high cadence, much higher cadence than we're getting from our ground-based surveys if you really want to probe the characteristic variability timescales of an intermediate mass black hole. But this light curve here is from TESS. Now, what does TESS usually do? Exoplanet transits, right? So it is designed to have exquisite photometry as well as really high cadence minutes imaging. So for something like a tidal disruption event, we actually, I forgot to show, we actually have some a TESS light curve of a TDE. That cadence is overkill because TDEs are very smooth. But for an AGN, which shows stochastic variability, and in particular for a very small black hole, you expect variability going down to very short timescales, to hours timescales. So TESS is actually necessary to do this experiment. So indeed, they had monitoring of this dwarf galaxy AGN, and you can see the blue is the source, and then in comparison to some calibration stars nearby. And indeed, you can fit the light curve and fit it with a damp random walk model and measure its variability amplitude as a function of frequency or time scale. And in fact, you measure a turnover time scale that is shown here. So the turnover time scale is, this is in log, but it's a few days, I think. No, it's fractions of a day. And it sits all the way over here. And so just as we expected, the time scale of this variability is very short. And if it actually connects with what you would expect from the black hole mass from the host galaxy properties. So indeed, this seems to be telling you that timing really is tracing the black hole mass, and maybe we can use timing alone to pick up the masses of black holes in galaxies. Does anyone have any questions on this? This is a really cool result. I do want to just point out that if we're talking about Rubin and we're talking about more standard big black holes, let's say 10 to the 8 solar masses, now we're talking about timescales on the order of 100 days, and we can certainly do that very well with Rubin light curves. Okay. This is an example of an AGN. And how do I know it's an AGN? Well, it had spectra with, in this case, I think it was dominated by narrow emission lines. So technically it would be considered a type 2 Seyfert galaxy because we don't see the broad emission lines, we only see the narrow emission lines. But they have line ratios indicating that they're photoionized by an AGN continuum. But it showed a large increase in its flux in the optical and the UV, and it was sort of smooth looking. During its flaring, it also had a dip in its X-rays, and it also had an increase in its broad emission line flux. So people were excited that this is sort of an AGN turning on. And one of the questions is, what is causing this large amplitude flare in this AGN? And because it was tantalizingly similar to this t to the minus 5/3 power law decline that you guys were fitting in your module yesterday, it was argued maybe this is a TDE in an AGN, which we were hearing about earlier this morning. And here is a zoom in on the optical light curve. This is from Atlas. And you can see that it seems like a very smooth, large amplitude flare. Well, this is kind of fun. This is the TESS light curve of this transient during its flare. And you can see that when you change your cadence from a few days to now minutes, you can see that there's a lot of structure in this light curve. And in fact, all of this structure is much more characteristic of this stochastic AGN variability than the sort of very smooth properties of a TDE flare. So this, I think, would be an argument against, or they use this as an argument against the flare in the AGN being due to a TDE. And what's fun is, again, you can use this beautiful light curve to measure the characteristic turnover of its variability timescale, and you get a black hole mass that I think makes sense based on the host galaxy properties. Okay, so in our hunt for tidal disruption events with ZTF, we've really come across some exciting behaviors. And it's really important, as you guys are transient hunters, to know that as you sort of zoom in on the nuclei of galaxies, there are a couple of realities to know. One is that supernovae also go off in the centers of galaxies. AGN are in the centers of galaxies, and of course, tidal disruption events are in the centers of galaxies. But the one thing that we also uncovered, which we weren't expecting, were examples of extreme AGN variability. So this is this cartoon picture that we saw this morning that Barry explained, where you have these multiple components for an AGN. And this cartoon picture was developed to explain why there were two spectroscopic classes of AGN. Why did we sometimes see broad lines and narrow emission lines? And then why did we sometimes only see the narrow emission lines? And so the way to sort of unify these objects, they were all coming from the same system, but it depended on the viewing angle of whether or not you could see the broad emission lines coming from the very inner regions of the accretion flow that weren't otherwise, but whereas at other viewing angles, that view was blocked by the dusty torus, causing the type 2 Seyferts. So the idea is this difference in spectral class is a geometric effect. It's a viewing angle effect. So you really don't expect an AGN to change between a type 2 and a type 1 or vice versa, because that would imply that suddenly your viewing angle to the AGN system changed, and that's not very physical. So that's why this class of changing look AGN was such a surprise, because indeed, one of the first big samples came from the Sloan survey, where they found that if they looked like at certain variable objects and looked at multiple epochs of spectra, there were some cases where an AGN Originally, okay, these are the appearing, yeah. Originally in Sloan had no broad emission lines, especially in H alpha and H beta. And then maybe how many years later? Let's say 5-10 years later, suddenly you see a second spectrum with BOSS at the BOSS spectrograph, and suddenly the broad lines had appeared very strongly. So it really appeared that these quasars were changing their spectroscopic class from type 2 to type 1. And it was also accompanied with variability of the continuum from these sources. They also see the opposite case, where you see a fading continuum. And when you look at multiple epochs of the spectra, where you originally had very strong broad emission lines, suddenly they disappear on timescales of years to be more like a type 2 spectrum. So this now is sort of challenging our understanding of what causes these spectroscopic classes. Why do we sometimes only see narrow lines? And also what is driving this dramatic change? And since Grisha is here, I wanted to make sure that I showed his recent results from a new, even larger sample of changing look AGN that has come from the Sloan 5 survey. And that has, I think, over 100 CLAGN in it. And so with these large samples, you can try to start looking at their properties and trying to figure out what is driving these large extreme changes that we think are due to changes in the accretion state in these systems. And so one of the interesting takeaways is that the black hole, it doesn't seem to care about what the black hole mass is. So it doesn't really seem to be something related to TDEs where you would be very wary of very massive black holes. They're still happening in those more massive systems. But there does seem to be a trend that you see a higher fraction of changing look AGN in the lower luminosity and lower Eddington ratio systems. So that might be telling you something about what's driving these state changes.
Suvi,
yes.
Just a quick point around that. As you go to higher supermassive black hole mass, if you disrupt more massive stars, you can still get TDEs. Just to add that point.
Yes, I mean it depends on the mass of the star, but then those are going to be more rare. But yes, you can push the upper limit a little bit. Yeah. Here is a really fun example of a changing look AGN that really blew our socks off. So here's an example. This was a variable, a source in IPTF, which was a precursor to ZTF. And it showed variability in its light curve, and it was a nuclear source. And when we looked at its archival Sloan spectrum, it really looked like it was a quiescent galaxy with some really faint, narrow emission lines that you really had to carefully dig into to find that would indicate that it has emission line ratios that are consistent with what we call a low ionization nuclear emission line region, which could be ionized by a faint AGN or also potentially stellar processes, but is sort of one of these hallmarks of a very weakly accreting black hole. And then this is what the spectrum looked like after we took a spectrum in 2016 when we saw this variability from this source. So this is completely transformed. It went from being dominated by stellar light with a very few weak narrow emission lines to now suddenly having booming broad emission lines characteristic of a type 1 quasar as well as a blue continuum. So that is a really dramatic transformation on the time scale of a decade. And one of the interesting things about it is if you look at this spectrum, it looks very much like a normal quasar, except its O3 emission line, which is a narrow emission line, is in its on state is still very weak. And so this is telling you that this narrow emission, which is thought to come from gas further out from the supermassive black hole, actually hasn't had a chance to respond yet to this large amplitude change in the continuum. And so one way to trace these systems is to look for where your H alpha luminosity is really high, but your O3 is actually suppressed, which is what we see. So we then looked systematically with ZTF, specifically at galaxies that had liner spectra. Now, liners are actually one of the most common type of galaxy spectra, but we specifically matched galaxies with pre-existing spectra from Sloan that consisted with liners, and then matched it with nuclear variable sources in ZTF. And we found another 6 sources where when we took a spectrum, I mean, it's so wild. The orange is the archival liner spectrum where you see mostly stellar continuum and a little bit of narrow emission lines. This one has a little bit of a broad component here. But then you look at the blue spectrum, which is after they were variable, and they've completely transformed. They have these booming broad lines and blue continuum. So we called this class of sources changing look liners. And again, these diagrams are showing what their pre-flare narrow emission line ratios said that they were. So these were kind of like on this borderline between Seaford and liners. They were very weak AGN, and now here they're really unequivocally quasars. And then this is just showing you what their light curves look like. So some of them show big sort of flaring activity, but some of them show more stochastic variability. And then now, if you compare these sources with the previous samples that had been discovered of the changing look quasars, the types of increases we see specifically in the broad lines is way stronger than in the changing look quasars, which are shown here from previous samples. So these are just really, really extreme. Sorry. And then here's some examples where we can go back in the archives and look at light curves of these sources, not just in ZTF, but looking back with Assassin and CRTS, and we can try to see when did they really turn on, which is shown with the X marks. So when we think their accretion really started to ramp up. Okay. And then you can start trying to understand, you know, what is it about these sources? Like what condition were they in to enable these major state changes? And you can look at their luminosities and their black hole masses and Eddington ratios, and you can see that they seem to populate a certain area of sort of this low Eddington ratio accretion space that could be potentially a symbol of the necessary conditions for these big changes of state. But there's still a lot to be understood of what is driving these dramatic changes. So ignoring the physics behind what's causing these quasars to turn on so dramatically, what can we do with these fabulous spectra? So one of the fun things about changing look AGN is you really get 2 chances to see the AGN. You get to see it when it's faint and you can actually see the underlying host galaxy light. And then you get to see it when it's accreting rapidly and see when the quasar is really bright. So we heard about this classic way of estimating black hole mass in AGN. And that's this virial method. where you take the width of the line, which tells you about the characteristic velocity of the orbiting gas, and then you use the radius that you infer for the broadline region. And Barry showed that we see a correlation between the luminosity of an AGN and its radius. And so you can use the luminosity, convert that to broadline region radius, and then you take the velocity of the broadline region, and then from that you get a black hole mass. So this is specifically for accreting black holes. But then I've talked a lot about these scaling relations where we use dynamical measures of black holes in quiescent galaxies to find relationships between the black hole mass and the mass or the magnitude of the host galaxy, or the bulge mass, or the velocity dispersion. So all of these relations require you to be able to see the galaxy. So this is what you can measure in the low state of these changing look AGN. This method requires you to see the AGN accreting. So you can actually, for the same black holes, right? The black hole mass isn't changing, it's just the state is changing. You can compare these various mass measures. And one of the fun objects is this first one, which actually has a quite narrow H beta emission line. It's actually what we call a narrow line Seyfert-1 galaxy. It's not actually narrow, it is broad, but it's narrower than broad, typical broad emission lines. And what's interesting is, if you were to take from the narrowness of its broad emission line, if you were to convert that to a black hole mass, you end up getting a black hole mass of only 10 to the 5.5 solar masses. Whereas if you look at the host galaxy properties, or even its host galaxy velocity dispersion, you would expect a much bigger black hole. So this is fun because people don't understand why narrow line Seyfert-1 galaxies have narrower lines. Some people have explained them as smaller black holes accreting at high rates. But another explanation is that it's a viewing angle effect. And actually the narrower lines is not because the black hole mass is smaller. So these are kind of fun ways in which you can use these objects to probe these scaling relations without even understanding why they're doing what they're doing. This is a really nice example of a changing look AGN that was discovered by Assassin. So here is the archival spectrum. I think this is called a type 1.8 Seyfert because it shows a weak broad H alpha line, but no broad H beta. So it's not a pure type 2. It's got a little bit of broad H alpha there. And you can see it might even have some interesting structure there. But you can see it kind of stayed in this relatively faint state. And then in 2013, it was caught by Assassin. And you can see that not only is it brighter, but now it has these classic broad, very broad bomber and strong bomber emission lines. And what they did was, when they realized that this galaxy had transformed its spectral class so dramatically, they monitored it across the electromagnetic spectrum, from the X-rays, the UV, to the optical, all the way into the near infrared. And with these nice light curves, they then tried to fit it with a model where it appeared that the X-ray variability was leading all the rest of the variability. And so they came up with what they call a lamppost model, which is to say that what if the X-rays are driving the variability, and then those X-rays are then irradiating the disk, and then the disk is then responding to that irradiation. So sort of reprocessing that X-ray radiation. And that sort of lamppost model, because of this temperature profile of the disk, which we saw before, you do expect the lags of the different bands to increase as you go to the longer wavelengths. And so that fit very nicely to the data. And Amy said, I have some slides on continuum mapping, reverberation mapping, and they had lots of emojis, so I thought I would show them. Where again, we saw the equation for this temperature profile of an accretion disk, but you can also represent with emojis that you have hot in the inner regions getting cooler to the outer regions. And in this sort of echo mapping, in this lamppost models, you have the X-rays coming from this corona that's vertically extended a little bit so we can irradiate the disk. And then you have different travel times based on the different annuli of the disk, wavelengths are corresponding to which parts of the disk. So you get these different lags. To your telescope. Okay. So those were changing look AGN, where specifically I'm referring to AGN whose spectral class changed from type 1 to type 2 or back. These are not changing look AGN. I don't know if they changed look because for most of them, I don't have a spectrum from before they did their thing. However, when I take a spectrum now, they all, to me, look like AGN. I call them AGN because they have broad emission lines. They have strong O3 emission, and some of them have some more unique features like helium-2 and Bowen fluorescence features. But in general, they seem like classes of accreting supermassive black holes, AGN. But what's really unique about them is that they have very large amplitude smooth flares, which really, when you first look at them, a supernova person would say, oh, that looks like a superluminous supernova. A TDE person would say, oh, that looks like a TDE. But you say, no, guys, it's something else, because these are AGN. Now, in particular, they all have the same property that the widths of their bomber lines are a little bit narrower. So these are all classified in the classification scheme as narrow line Seyfert 1 galaxies, which again is this interesting subclass of AGN. So there seems to be a connection between this subclass of AGN and producing these very smooth optical flares that we were picking up with ZTF. Has anyone heard of Scary Barbie? Good, great marketing. This is an example of an incredible name. I mean, I guess Anna, she was here yesterday, but Anna Ho studies LF bots. They have fun names like the cow and what are the other ones? Koala, camel, and they're all derived from their names, right? Sort of, their ZTF names. But this one, cleverly, you can see its ZTF name, which, now most of our transients, we use the AT name, the astronomical transients name. But this one has a fun one because it sort of looks like Barbie. So, and it's definitely scary because it is a very luminous, smooth transient. And if you study superluminous supernovae, even you will be shocked at how luminous this transient is. And it's very, very luminous, way out of the ballpark for supernovae. And it has properties that look a lot like an AGN. And however, its lines actually are quite narrow, but they do have a broad base. But this is sort of in this confusing territory of potentially extreme AGN behavior, but we don't have a pre-event spectrum to really know, did it change look or has it always looked like this spectroscopically? It was accompanied by X-rays that look a little bit like an AGN. So this is one of those confusing objects. And it happens to also, I think, have been localized with a neutrino, just for fun, so.
Just to tie it into this
Yeah.
morning's lecture. So this is a great point. So this flare is a factor of 500 times more luminous than a type 1A supernova. There are very few things that can generate that amount of energy. So you should be thinking in terms of weird events like massive stars being shredded or GRBs or whatever. You need to deliver that much energy. That is not a simple gas fluctuation process. Something weird happened there.
Definitely. There is an artist's impression of that weird thing, some sort of gas, or potentially a star disrupted in a gas disk.
What are some models? Like, are there theoretical models that can explain this light curve that have been proposed?
So I think it all comes down to how do you have such a smooth, rapid accretion event of so much gas? And so I think the argument is potentially a disruption of a star in an AGN disk. But this certainly isn't, there's AGN activity going on in this source. It's got AGN components, but maybe the source of the gas came from a disrupted star in the AGN disk. Here's another example known as Ansky, again, I think because of its fun ZTF name. But it showed dramatic variability that was picked up by ZTF and showed sort of an interesting change in its spectrum where here's the Sloan spectrum. You see some weak narrow line emission. And after this flare, you see, I think, an enhancement in O3, but there's not a lot of change in the spectrum, but there's some enhancement in the narrow lines. And so this was sort of interesting. That it originally was published as an awaking up black hole, awakening of an AGN, because it sort of showed previous activity and then sort of this turning on. But what's amazing is with X-ray monitoring, it was revealed to have a QPE. So one of the conclusions of this paper was, okay, we've talked a lot about this exciting connection between TDEs and QPEs, that TDE disks, which are newly formed from a disruption of a star, could be illuminating some sort of orbiting star that then collides with the disk. So this might be a similar phenomenon where somehow you're increasing the accretion rate onto this black hole, and then again, it's interacting with a star that was already there near the black hole orbiting. But this is really fun and beautiful source. So I guess this would be an argument for Rubin is going to do something like this extremely well, but we got to have our X-ray satellites as well so we can pick up these phenomena. So we have to work together. Okay, so now I'm going to talk about how we won't talk about the physics of the variability, which I think is a very interesting topic, but is a source of debate in the community. And let's just use this stochastic variability just as a signpost for black holes in galaxies. In this case, we really are trying to find these intermediate mass black holes that we think should reside in the nuclei of dwarf galaxies. And so this was a search by my former student, Charlotte Ward, who's now a professor at Penn State. And she did very careful, custom, deep difference imaging in the centers of a sample of over 100,000 dwarf galaxies with ZTF, and also show we did it in the mid-infrared with WISE. And she did careful cuts to specifically look for stochastic variability characteristic of an AGN. And remember that as we go to these smaller black holes, we need to be probing these shorter timescales. So it's really important to have a good cadence, but ZTF is a cadence of 2 days in the GNR band. So it's definitely, we think, sufficient. So here are some examples of this very careful, faint variability that we see in the centers of dwarf galaxies. And then we look at our candidate AGN in these dwarf galaxies and their host galaxy masses. And we're starting to probe these very low mass galaxies and showing that they in fact have an AGN. And just as a warning, as all of you go out there trying to find either AGN or tidal disruption events, don't forget about the supernovae because they are there. And so even in the centers of dwarf galaxies, you are going to sometimes just pick up a supernova that happened to have gone off, even though if you're doing aperture at the very center. So we had to carefully visually rule out anything that was obviously a supernova. So then, yes?
Question. So when you go to really low mass black holes in the dwarf galaxies,
yeah,
is there a risk for contamination from just your massive stars hanging around and doing?
Oh, like an LBV eruption?
Yeah, yes.
I'll show you one.
Okay.
Yeah. Yeah, in general, dwarf galaxies, as you go to these lower mass black holes, everything is harder. Accretion signatures are harder because you have to worry about, like in the X-rays, you have to worry about X-ray binaries. So everything gets harder. Variability, though, potentially is unique enough that you can distinguish. Then this is now looking in the mid-infrared, which is probing sort of sources that otherwise would be obscured in the optical. Again, looking for variability that's stochastic, and then seeing which we have a sample of the dwarf galaxies, which showed mid-infrared variability. And what's really interesting is if you had just taken the spectra of these galaxies and looked at their emission line ratios, you would have thought that they were just star-forming galaxies. So you would have had no idea that, in fact, there was an AGN in the center because their line emission is dominated by star formation, and so they would have been totally missed by spectroscopic survey. And so we found 44 ZTF selected and 158 Ys selected intermediate mass black hole candidates, indicating an active fraction of 0.2% of all dwarf galaxies. And then here is zooming in on our lowest mass systems. These have evidence of an AGN, and the blue circle shows the location of the AGN, of this variable source. And these have masses less than 10 to the 8 solar masses, the galaxy. So if we look at these relations between galaxy mass, oops, and black hole mass, oh, this is a typo. This should be, should be a galaxy, maybe it's a G, or a star. Galaxy mass and black hole mass, if we go down to 10 to the 8 solar masses, now we're really tracing this intermediate mass black hole regime. So this might be a potential exciting application for Rubin to do this in an even bigger sample. Okay, so when you start looking off the nuclei of galaxies, you are going to pick up, now, of course, you're going to pick up supernovae. Okay, they are definitely all over the place. But what if we looked at off-nuclear sources that were not supernovae, but were stochastically variable, behaving like an AGN? And this could be a way to actually find supermassive black holes that are in the process of recoiling from a merger of two massive supermassive black holes. And so this would be sort of a way to pinpoint these byproducts of gravitational wave mergers of massive black holes in galaxies. And so Theoretically, a supermassive black hole merger can result in recoil kicks of up to 5,000 kilometers per second. And it's been calculated that if this black hole continues to move out into the galaxy, that it actually could continue to accrete gas bound to it and be observable as an AGN for up to 10 to the 7 years. So this might result in a population of accreting AGN that are actually offset from their galaxy nuclei. And this actually could be observable because this corresponds to offsets in the local universe of tenths of an arcsecond. And we can certainly do that with Rubin and other ground-based telescopes. And here's one of the first exciting candidates for a recoiling black hole, where you see a source that's varying and it's off nuclear. And it is not clear. It could be a recoiling AGN, but also could be an eruptive luminous blue variable or some sort of very peculiar type 2N supernova. I think the most recent analysis favors luminous blue variable. Okay, so we looked specifically for stochastically varying sources that were not in the centers of galaxies. And again, Charlotte did this careful forward modeling where she could determine using the ZTF images to find where the variable source was, then use the deep imaging to really do force photometry to make sure you're getting the light curve of the variable component and measuring its offset. And so here are some examples of sources that showed the properties of an AGN in their light curves, but were actually spatially offset from their host galaxies. And so you see the image and the model of the image and then the residuals. And so these were all considered recoil candidates because they were offset from their host galaxies and they had, in fact, spectra consistent with a quasar. We did another fun experiment with pan-stars where we didn't have as beautiful light curve information from pan-stars, but we did have enough epochs that we could look for what's been called in the literature something called varastrometry. So looking at how the position of a source varies with time. And remember in the beginning of the lecture, I told you that AGN are bluer when brighter. So if you have a source with a variable AGN and the AGN is not in the center of the galaxy, then you would expect the centroid of the galaxy to shift. So if when it's very bright, the centroid of the galaxy would shift here, whereas when it was faint, it would be more here. So we looked for galaxies where the position of the blue peak shifted with time. There was a scatter in it, and the blue peak was offset from the red peak, and the red filters are tracing more of the stellar light. So here's an example of a source. This is a kind of fun source because by eye, you're like, oh my gosh, that's beautiful. But we didn't find it by eye. We found it using this variability of the astrometry of the centroid of the red and bluer filters. But you can see there's clearly a blue source that's offset from its host galaxy, which is redder. And when you take a spectrum of the source and its galaxy, indeed the blue source is this booming quasar, but it looks like the galaxy itself also has a faint Seyfert 2 spectrum. So it also has narrow lines powered by an AGN. but this quasar is offset from the galaxy by 1.8 arc seconds, which is 6.7 kiloparsecs. And so what produced this AGN offset from the host galaxy? So there are a couple scenarios. Maybe this black hole is recoiling from a merger that happened in the center of that galaxy of two black holes. The problem is we don't see a large velocity offset of the broad lines of the quasar. So we don't really see evidence for a lot of radial motion. And then we also have evidence that there is actually an accreting black hole in the host galaxy, the red galaxy. So in a recoil, you wouldn't have a black hole left in the center of the galaxy. Another option is that the black hole is actually being slingshot after interacting with a binary black hole in the center of that red galaxy. But again, we don't see any evidence for big velocity shifts. So finally, the slightly less exciting version would be that this is a dual AGN, so that in fact, this quasar, underneath it, there is some sort of host galaxy, which we do careful difference imaging. We can sort of put upper limits, but we can't totally rule out the presence of a host there. And so in fact, this is sort of tracing the interaction between galaxies. And we have some numerical cosmological simulations of galaxy interactions and with black holes that can sort of produce some of the properties of this system. Okay. So we've talked about intermediate mass black holes, and we've talked about recoiling black holes. So last topic I want to talk about is binary supermassive black holes. And of course, we know that galaxies collide and interact in the universe. And we know that almost every galaxy has a supermassive black hole in its center. And so you expect these black holes, when galaxies merge, to eventually become gravitationally bound and form a binary that eventually merges with through gravitational wave radiation. So there are a lot of people interested in finding binary supermassive black holes in the universe. And of course, in the future, we're going to have a gravitational wave perspective of these black hole mergers. But in the meantime, there have been various arguments for electromagnetic signatures of binary supermassive black holes. And one potential hallmark of a binary supermassive black hole is the characteristics of circumbinary accretion. So if you have an accretion disk around this binary supermassive black hole, you expect certain sloshing and torques that cause periodic accretion onto the black hole. And so if you were to take the power spectrum of this variability associated with the accretion onto these binary black holes, you might get a characteristic strong periodicity at certain frequencies that relate to the mass of the binary system. So astronomers love looking for periodic signals. And so with pan-stars and other long baseline surveys, we have been looking for periodically varying quasars that might be a signature of a binary system. And so shown here are some examples of candidates that have been published in the literature. And I just want to show you sort of the basic arguments for why we think these optical surveys actually have the sensitivity and area capable of actually detecting binary supermassive black holes. And in particular, the timescales being probed by these optical surveys like ZTF and Rubin and pan-stars are in the regime where we might even see the black holes in the close enough that they're actually emitting gravitational waves. So LSST in particular really has the depth and the area that we think is above this curve and actually is sufficient to detect accreting binary supermassive black holes. And so with try to do this with pan-stars. This is something that you could do right away with, well, not right away, but maybe after a few years of Rubin data. We simply took the optical colors, which you're going to get from Rubin, and we selected point sources that were in this color region of quasar. And then we sifted through, let's see, how many quasars did we look at? Over 9,000 quasars, sifted through their light curves and specifically looked for light curves which showed evidence for periodic variability. And so here are some of our candidates, and a lot of these sources ended up failing later as we continued to monitor them, and these initial what seemed like periodic trends did not persist. But here's one of our examples, and here is a famous example. I really like the title of our paper, which was "Did Assassin Kill the Supermassive Black Hole Binary Candidate PG1302?" Because it had come up in CRTS, pretty long baseline CRTS data as this potentially periodically varying source. But then as we continued, as it was continued monitored by Assassin, this simple periodic variability did not persist or had shifted. Yes.
So just on the sample that Matthew put together that included PG1302. So just for context, folks, so there was an original sample in which this periodic AGN was found. There were 111 AGN in it. And so what we've done is we've kind of tracked the behavior of these things over time. And as Suvi's showing, right, sometimes you lose periodicity. So you see hints of periodicity, and then it goes away. So of the original 111, half of are no longer periodic, right? So we're slowly destroying the number of binary supermassive black hole candidates in AGN. Well, we're maybe seeing some interesting quasi-periodic behavior going on. Essentially, in a real sort of, live universe, we might expect 0, 1, or 2 periodic signatures, kind of like this. We don't yet know what universe we live in. But.
Yeah, and one of the advantages of Rubin will be its 10-year baseline, and I think, maybe we should probably be arguing that we want to be also, taking these long baseline light curves from ZTF and CRTS and Assassin and really kind of projecting them through. I don't think I have the, I don't have the figure here, but there was a nice paper that showed that when you have this red noise, this stochastic variability in AGN, it's very easy to mimic periodicity over a couple cycles, but really hard. Once you get to like 10 cycles of a period, it's really hard to get that stochastic variability to look like a period. So the more cycles you can sample, the more robust your significance, and the stronger you can actually claim that it really is periodic. So the best case for Rubin would really be, you really want to be finding these shorter period systems with these really long baseline light curves. Okay, so I'll just wrap up with what I think is going to be a supermassive black hole treasure trove from LSST. And we've really used IPTF and pan-stars and ZTF as sort of a sandbox to show how time domain observations can start probing the extremes of supermassive black hole demographics. And I think Rubin is going to be really exciting for continuing to look at these exotic systems and using variability as well as TDEs to pinpoint binary supermassive black holes, intermediate mass black holes, spinning black holes, and offset AGN from recoiling supermassive black holes. And I'll just finally conclude with, since Eleanor Rossi is here and she is a part of the LISA consortium, they're gearing up to be detecting binary supermassive black holes between 10 to the 5th and 10 to the 8th solar masses through gravitational waves. And both the mass range as well as the redshift range that they're going to be probing are very complementary to the TDEs that I was talking about yesterday. And so this is going to be a really exciting time where we're getting all this time domain discovery of black holes, but we can then combine that with what we're learning from gravitational waves from LISA and nanograv at higher masses. All right, I think I will wrap up there and we can have some discussion if there are certain topics that seemed exciting or if you have questions.
Thank you, Suvi, it was great. I always learn from you. So, but one thing that I haven't understood in general, what are the plans for LSST in the 2030s? Thinking about LISA detections and simultaneously LSST kind of
So I know
instrument.
even before then that in their official document, they recommended a target of opportunity mode for LSST to be able to respond to neutrino alerts as well as gravitational wave alerts. Probably for LISA, yeah, so if you were thinking of some sort of target of opportunity follow-up of LISA sources, I think that they will already have lots of experience in doing that. So I think if I understand correctly, after the 10-year survey, there will be a new sort of reaching out to the community of what to do next. So if you had good ideas for what to do for LISA, I mean, maybe we could discuss a little bit what would be good, but I think they're going to be open to ideas.
Thank you.
So I know changing like AGN are rather rare, but I guess at what frequency right now do we expect to see them given like a large survey like LSST? Like what do we expect?
So the, I mean, probably Grisha can give a projection on rates, but I will say the frustrating thing will be to really say it's a changing look, you really need a spectrum before the dramatic change to show that it changed spectrally. If you think that you just want to see, large fluctuations in the continuum, then Ruben will definitely do that. But you may be, if you really want to see how it translates spectrally, you're going to be limited to the spectroscopic samples. However, we have things like DESI and Sloan 5 and some other big spectroscopic samples. So there might be some great studies you could do using those as the baseline. Yes.
So I was wondering about the searches that were done just based on this stochasticity of the light curve. So for those objects, since the spectrum was normal, would you expect to see like X-ray emission from those too, or is that like a useful component to have?
Yes. So in the past, whenever someone proposed for so there are different ways you can try to find AGN and dwarf galaxies. So we use variability. You can also try to look for faint broad lines, but certainly X-rays would be detected. I'm trying to remember if we cross-matched with, I'm sure we cross-matched matched with existing X-ray catalogs, but you might need to do dedicated follow-up with Chandra or XMM to pick up the X-ray emission, which will be faint, but you can sort of calculate what you'd expect, and that would be a good study. I forget if we already looked at that, but definitely, yes, you would expect to see X-rays, albeit maybe faint X-rays.
Right. Any other questions? Actually, I had a question. So my recollection was that for Scary Barbie, there is no obvious host galaxy.
Right.
Has that changed?
Redshift.
Like, how do we know it's nuclear at all?
I think we have not seen the host galaxy light because it's so bright and high redshift. Yeah.
Okay. But so could it be something else?
If you can make that spectrum.
Okay.
It has these very like Lorentzian narrow lines with a broad base.
Right.
That might be a good JWST proposal. Get the
I'm pretty
underlying
sure
host.
somebody would have tried it.
You think so?
Yes, yes.
But that would be interesting to get the black hole mass.
I mean, the transient's still going, like we're still in the spectra of it.
Yeah. Right.
And it still looks like these spiky lines.
Yeah, I mean, the only thing that can look like this is probably some exotic superluminous type 2 supernova.
Right.
Yes. That's the only thing I can think of. Yeah, but yeah, the reason I asked this was because one of the things I wonder is, like in the LSST era, when you're seeing further and further events,
yeah,
like is it obvious whether something is nuclear or not?
Yeah, I mean, I think Mitchell is studying higher redshift TDEs, and often the TDE can outshine the host, so it'll look more like a mini quasar. So yeah, you can no longer rely on the position, but then you're going to have Roman, which is going to provide this exquisite space-based spatial resolution. So then I think you can start using nuclearity quite well.
Just on that, so a really important problem, right, is you could have a flare superimposed on an AGN, which could, for example, correspond to a supernova or something else going off in a nucleus. It doesn't have to be associated with the AGN itself, right? So you know, we want to be able to disentangle these things, but we won't have the angular resolution for distant things to say for sure.
Yeah, and some of the original dwarf AGN searches that looked for broad lines, they were very clever, and they went and took another spectrum later just to confirm that the broad line was still there. And in some cases, it was in fact from a supernova that happened to be in your spectrum producing the broad lines. So you have to be very careful.
Right. Any other questions? Who all here work on AGN? Okay, just one person. Okay. Okay, 2, 3. Okay, yes. Okay, good. Okay, there's a good sample.